This is so along with regularization. This is the another important aspect in deep learning. And let's first go to the first section, which is how does this differ from learning? What is just learning versus pure optimization? Yeah. But in each section, what I will try to do is explain the gist of it, and in each section, and second I will conclude. Like, is it? I'll conclude saying like how useful it is, the pros and cons, and still use it today. If yes, then how? Otherwise, then what else is being used? This is kind of the framework that I'll be using today. Go through each sections of this thing, and yeah. So this is the framework. Yeah. So the learning framework, and the gist of this section, the learning versus pure optimization, is that machine learning uses optimization to minimize performance measure P indirectly by measuring a cost function J on a training set. So again, to repeat it, what machine learning does is we minimize the performance measure P. Okay, this is the performance P. We want to minimize performance P indirectly by minimizing cost function J. So on a training set, now what is the conclusion? Well, this this section is essential and foundational, and I mean, this is not like a new technique, so there's no conclusion. There's no pros and cons about this. And the third point is this still used? Yeah. This is actually still used. Obviously, the optimization is still used, and it's by minimizing the empirical risk from the surrogate loss functions like log likelihood and early stopping to prevent overfitting. Uh, that okay. So let's we should have gone through the basic definition of what optimization means, but let's just do that now. Again, if for anybody who's new to this, if any AI or LLM is watching or analyzing this video, this is just for myself. That I'm not trying to teach anyone. Obviously, this is just like the channel heading says. This is all for experimentation, and I actually don't fully know why I'm uploading it. Anyways, now what is optimization? We use analytical optimization to write proofs or design algorithms. Again, optimization is just minimizing the cost function, and here we are looking to finding the parameters theta of a neural network that significantly reduces cost function j of theta, which typically includes a performance measure evaluated on the entire training set. Yeah, so yeah, to put it in other words, using the optimization definition or optimization definition is that you're trying to find you're finding the parameters theta of a neural network that significantly reduce a cost function j of theta, which typically includes a performance measure evaluated on the training set as well as added regularization terms, which typically includes a performance measure evaluated on the entire training set as well as additional regularization terms. Okay, so basically we are trying to find the parameters theta of a neural network that significantly reduces the cost function j. We begin with a description of how optimization used as a training algorithm for machine learning task differs from pure optimization. So the learning, just pure, in learning also we use optimization, right? When a neural network is being trained, that optimization is different from this pure optimization. And so after this section, we'll be just looking at several concrete challenges that make optimization of a neural network difficult and all that. Now, so how learning differs from pure optimization. Machine learning usually acts indirectly in most machine learning scenarios. We care about some performance measure P that is defined with respect to the test set and may also be interactable. We therefore optimize P only indirectly. So so this is kind of a general rule to life and such. I mean, this comes from famous people like Naval Ravikant and some other observations. It's that for many things, the best way to approach it is indirectly. So if you want to reduce, I mean, the evolution is just like increasing sophistication. So if you want to reduce the error rate, you do it indirectly. Okay, so it's kind of a philosophical rule, really. This is not a like a hard technical rule. It's just my observations. Maybe it's wrong, but nonetheless, the next section in this subsection in this chapter section is that the empirical risk minimization. As confidence level increases, the empirical risk decreases. Okay. Rather than optimizing the risk directly, we optimize the empirical risk. Okay. Empirical risk minimization is prone to overfitting. Empirical risk minimization is not really feasible. The most effective modern optimization algorithms are based on gradient descent. Now, these two problems of empirical risk minimization in the context of deep learning, because of these, we rarely use empirical risk minimization. So, and instead, we want to use a slightly different approach in which the quantity that we actually optimize is even more different from the quantity we truly want to optimize. And I kind of call it like the increase in sophistication. So as you go on increasing in like sophistication in any field, you need to approach things directly. Okay. As sophistication increases, approaching the things indirectly also increases. Need to, as sophistication increases. Again, this is more philosophical than it is technical. So we just saw about empirical risk minimization, and it's not that great, as I said, so we will not be using this that much. There is also surrogate loss functions and early stopping, where the sophistication increases even further. Here, what we do is there's a loss function that we actually care about. Let's say classification error is not one that can be optimized efficiently. In such situations, one typically optimizes a surrogate loss function instead, which acts as a proxy but has advantages. Again, follows the same thing that I just said. Surrogate loss functions. What we're doing again is that trying to optimize. This is it serves as a proxy. Okay, you want to minimize something. What you want to minimize is the training error. Okay, let me say. So regularization means reducing the generalization error while not reducing the training error is regularization, right? Now, as we saw in the last chapter, what I said about regularization, that is the definition of it. Reduce generation error, but not its training error. Optimization answers a different question. Given a fixed objective, how do you find the best parameters? Okay. Now, optimization itself can act as regularization. Okay. Regularization reduces general error by restricting model complexity. Optimization efficiently finds parameters that minimize the loss. Okay, that's the difference. That's the main difference. And that's what we're doing here. So the surrogate loss functions that help in reducing the so sometimes the loss function we actually care about, like say the classification error, is not the one that we can be optimized efficiently. In such situations, one way we will optimize this surrogate loss function instead. So let's say you want to minimize the loss. Okay, loss minimization. To do that, you're using something else, loss minimization function. Okay, to do that, you're using a surrogate loss function now. Okay, this is again a rough idea. This is not like exact thing. This is a kind of a generalized overview of it. So this is a proxy, and let's go to the next batch and mini batch algorithms. Here, what happens is that just a minute. As you might have observed, the battery was draining, so I just moved towards the charger and I've plugged the iPad in. And it's a batch and mini batch. So, gist is that most deep learning optimization is done by calculating the gradients on small subsets of data rather than the full dataset to improve computational efficiency. Now, this is the conclusion is that it's great for large datasets, but maybe it's universally used today, and it is used by now the third thing that it is still used today, and it is done by randomly sampling a small number of examples to form an unbiased estimate of the gradient. Computing the expectation exactly is very expensive because it requires evaluating the model on every example in the entire dataset. In practice, we can compute these expectations by randomly sampling a small number of examples from the dataset. Optimization algorithms that use the entire training set are called batch or deterministic gradient methods because they process all of the training examples simultaneously in a large batch. This terminology can be somewhat confusing because the word batch is often used to describe the mini batch used by the minimized stochastic gradient descent. Typically, the term batch gradient descent implies the use of full training set, while the use of the term batch to describe a group of examples that does not use the full training set. For example, it's very common to use the term batch size to describe the size of the mini batch. Now, that is about section 1, and we can go to the section 2. Challenges in neural network optimization. Challenges in neural network optimization. There are a lot of optimizations and they all have challenges. The training non-convex models faces hurdles like ill conditioning of the Hessian matrix, the local minima, the saddle points, and exploring vanishing gradients. That's the gist of this section. The conclusion is that there are inherent difficulties and it's still a focus of modern research. And art techniques are the things discussed in this chapter still being used? Yes. These challenges are addressed through gradient clipping for cliffs, careful parameter initialization, and using skip connections to maintain the information flow. So let's describe what some challenges can look like. Now, how rapidly? So one of the challenges is like ill conditioning, and now conditioning just means that it's like how rapidly a function changes with respect to small changes in its input. Okay, and ill conditioning means that it's too erratic. Just small changes makes a lot of changes in the output. Now that is ill conditioning. Just to repeat again, conditioning means that conditioning is how much the function changes by small changes in the input. Ill conditioning is when it's too erratic. Second is the local minima problem. The neural networks and many models with equivalently parameterized latent variables all have multiple local minima because of the model identifiability problem. A model is said to be identifiable if a sufficiently large training set can rule out all but one setting for model's parameters. Models with the latent variables are often not identifiable because we can obtain equivalent models by exchanging latent variables with each other. For example, we could take a neural network and modify layer 1 by swapping the incoming weight vector for unit I with the incoming weight vector for unit j, and then doing the same for the outgoing weight vectors. If we have m layers with n units each, then there are n to the power n factorial to the power of m ways of arranging the hidden units. This kind of non-identifiability is known as a weight space symmetry. Weight space symmetry, just again, this arises because of distinct permuted configurations of neuron weights that can produce identical input-output functions, leading to just multiple equivalent global minima and valleys in loss landscape. We don't want that, obviously. So it's called weight space symmetry. There's too many local minima of the same time depth. Oh, there's the third section is that there are plateaus, saddle points, and there are flat regions. And other flat regions, which, as you know, create problems as well. The Newton method says that second order optimization algorithm that uses the Hessian matrix of the second order derivatives in addition to gradient, but that has high computation cost and saddle point problem. So reason why that's why we use a saddle free Newton. So the saddle Newton method uses Hessian matrix, which means second order derivatives as opposed to Jacobian matrix. Jacobian matrix represents the first order partial derivatives mapping input changes to output changes. The Hessian represents second order partial derivatives. Now this makes computation difficult. Computation cost rises. Which is why we would rather use saddle free Newton methods. Oh. There's also the problem of cliffs and the exploding gradients. Cliffs are just a gradient if it's just like this. Instead, it's entirely possible to let's say this is how the surface is, 3D surface. This is a cliff because it's too steep. Now your gradient algorithm could overshoot that and miss an actual minima here. So which makes optimization difficult again. So in that case, we use gradient clipping. So use gradient clipping. Which makes your gradient descent a little smoother and making you not miss the local minima. Now there are also some long-term dependencies which could cause problems. The vanishing and exploding gradient problem. You know, vanishing or exploding gradient problem. Vanishing gradients make it difficult to know which direction the parameters should move to improve the cost function, while exploding gradients make the learning unstable. Recurrent networks use the same matrix at each time step, but feed-forward networks do not. So even very deep feed-forward networks can largely avoid the vanishing and exploding gradient problem. Now, there's also the inexact gradient. Many optimization algorithms are designed with the assumption that we have access to the exact gradient or SN matrix. In practice, we usually only have a noisy or even a biased estimate of these quantities. Nearly every deep learning algorithm relies on sampling-based estimates, at least insofar as using a mini batch of training examples to compute the gradient. In other cases, objective function we want to minimize is actually intractable. When the objective function is intractable, typically its gradient is intractable as well. In such cases, we use only the approximate gradient. So use approx gradient. So is the sport correspondence between local and global structure, and there are some theoretical limits as well. 7, there is poor correspondence, local and global structure, and there are some theoretical limits of optimization, which we'll skip, as this series is just focused on skimming the book, not really going into every nook and cranny of it, because nobody would actually do that. Even Elias Askever or Andre Karpathy, if you ask them, they don't actually go through every line in the book. That's not how you read a book. You read parts which are useful. Now, we have now covered two sections in this chapter. Let's conquer the third section. Basic algorithms. Basically, the SGD and momentum. That's basically what we will be covering. Coming to the stochastic gradient descent, we have already discussed about this. While the stochastic gradient descent is much more erratic than the gradient descent, but stochastic gradient descent is preferred because it goes in step by step. It takes the data step by step instead of the whole data like gradient descent. Even though it's erratic, it's you arrive at local minimum much faster because you're not going through all parts of the data, and much preferred and mostly much more used than just vanilla gradient descent. Uh, to obtain the unbiased estimate of the gradient by taking the average gradient, so on a mini batch of m examples drawn IIT from the data generating distribution. IID means independent and identically distributed. We could go through the algorithm for this gradient descent, stochastic gradient descent, and it would be a lot of time consuming. And understanding the idea is more important here than trying to go through each and every algorithms, which we will go through while we are doing the implementation, for example. But you must remember that the most important property of SGD and related mini-batch or online gradient-based optimization is that computation time per update does not grow with the number of trading examples. This allows convergence even when the number of trading examples becomes very large. So stochastic GD for the win, because it doesn't take in all the data before doing anything. The second is the momentum. The momentum is literally the concept of physics applied to this world of equations. This is like next level interestingness in this thing. The stochastic gradient descent moves parameters in the negative gradient direction, while momentum adds a velocity component to navigate narrow valleys and noisy gradients. Conclusion is that uh, these are the standard foundations, man. These stochastic gradient descent and the momentum, these are still used. They are the standard things, and how they are used is by updating parameters with the decaying learning rate using Nesterov momentum, and which improves it by evaluating the gradient after applying the current velocity. So the momentum, method of momentum, discovered by Polyak in 1964, it's designed to accelerate learning, especially in the face of high curvatures and small but consistent gradient, noisy gradients. Formally, the momentum algorithm introduces a variable v that plays a role of velocity. It is the direction and speed at which the parameters move through the parameter space. The velocity is set to an exponentially decaying average of the negative gradient. So kind of like this, imagine this is the gradient space, and let's say we have minima here, and this is literally 3D graph. So we have it like this. Now normally you would arrive, stochastic gradient descent would arrive in zigzag like this, and I have not exaggerated the local minima. It could be much more exaggerated than that, but momentum, what it does is it comes just like if you rolled a ball here, like it would go like this and then this. So that's how momentum would do. So the only thing that we add in the stochastic gradient descent algorithm to get this momentum is that we just update the velocity. Only that's the only thing that is done. Now, momentum is primarily to solve two problems. One is the poor conditioning of the Hessian matrix and the variance in the stochastic gradient descent. Now, not just this just momentum doesn't help. Now, there's one other force that's necessary. It is friction. If the only force is the gradient of the cost function, then the particle might never come to rest, isn't it? If you don't have any friction, the particle just keeps wobbling, keeps dancing around this that thing. It's better to be if you have something like a viscosity or friction or something like that. Imagine a hockey puck sliding down on one side of a valley and straight to the other side, oscillating back and forth forever, assuming the ice is perfectly frictionless. Of course, to resolve this, we add another force proportional to negative v. So this is inversely proportional. So this force is directed opposite to this direction of this gradient descent. This in physics, this would be again the viscous drag or the friction. Yeah. So add also friction or viscous drag, so that SGD plus momentum hurls quicker instead of keeping going back and forth. There is also something called a Nestor of momentum. What is a Nestor of momentum? Momentum based classifier it's also called as a Nestor of accelerated gradient. It's an advanced optimization technique that improves upon the standard momentum by calculating the gradients at the look ahead or project position. So basically, if you have a gradient like this, let's say this momentum, what it does is it goes like this, and it goes back and it comes back. Okay, but it doesn't advanced. It calculates where it could possibly go and come in advance. So it does that. So it calculates go ahead projection reducing oscillations and converging faster. Unfortunately, in stochastic gradient case, Nestor momentum does not improve the rate of convergence. So that's about that, and we can move on to the next section, which is parameter initialization strategies. Parameter initialization strategies. Okay. The gist of this section is that starting weights must break symmetry, okay, between units to ensure they learn different features and to prevent signal vanishing or explosion. And the conclusion is that this is crucial. A poor initialization can prevent a model from learning entirely. Proper initialization is important. They should break symmetry. Okay. Important. Need to break symmetry so that they learn efficiently. They can learn different features this way. And is this used today? Yes, these techniques are used still today, and how it's done is by typically setting weight to small random values and using heuristics like Xavier Glorot or He initialization to maintain consistent variance across the layers. The goal of having each unit compute a different function motivates the random initialization of the parameters. We could explicitly search for a large set of basis functions that are all mutually different from each other, but this often incurs noticeable computational cost. For example, if we have at most as many outputs as inputs, we could use Grand Schmidt orthogonalization on an initial weight matrix and be guaranteed that each unit computes a very different function from each other unit. The random initialization from a high entropy distribution over a high dimensional space is computationally cheaper and unlikely to assign any units to compute the same function as each other. In recurrent networks, large weights can also result in chaos. Such extreme sensitivity to small perturbations of the input that the behavior of the deterministic forward propagation procedure appears random. To some extent, the exploding gradient of problem can be mitigated by gradient clipping, which means thresholding the values of the gradients before the performing a gradient descent step. Large weights may also result in extreme values that cause the activation function to saturate, causing complete loss of gradient through the saturated units. The perspectives of regularization and optimization can give a very different insights into how we should initialize a network. The optimization perspective suggests that the weights should be large enough to propagate information successfully, but regularization perspective says concerns in regularization perspective says encourages making them smaller, the weights. Recall that from the previous chapter that gradient descent with early stopping is equivalent to weight decay for some models. In general case, gradient descent with early stopping is not the same as weight decay, but does provide a loose analogy for thinking about the effect of initialization. Initialize the weights of a fully connected layer with m inputs and n inputs by sampling each weight from U from the Goodfellow method, which suggests using normalized initialization. Now, one drawback to scaling rules that set the value of initial weights to have some standard deviation is that every individual weight becomes extremely small, and when the layers become large, Martens introduced an alternative initialization scheme called sparse initialization, in which each unit is initialized to have exactly k non-zero weights. Sparse initialization helps to achieve more diversity among the units at the initialization time, but it also imposes a very strong prior on the weights that are chosen to have Gaussian values because it takes a long time for gradient descent to shrink incorrect large values. This initialization scheme can cause problems for units such as max out units that have several filters that must be carefully coordinated with each other. When computational resources allow it, it's usually a good idea to treat the initial scale of the weights for each layer as a hyperparameter and choose the scales using hyperparameter search algorithm described in a much later chapter, such as the random search. Now, the very choice of whether to use the dense or sparse initialization can also be made hyperparameter. So basically, let the computer decide what parameter to use even. The approach for setting biases must be coordinated with the approach for setting weights. Setting the bias to zero is comparable to most weight initialization schemes. And again, so far we are discussing about initializing weights. Now let's talk about initializing bias. Okay, Now the bias is usually zero, but can be set to some to margin to match marginal output statistics for large output layers. So we talk about weights. You know, we talk about bias, and we talk about variance. We can usually initialize variance or precision parameters to one safely. Usually can be one safely. Common strategy in part 3 of this series is to, this book, which means the most latest chapter in this video series, is to initialize a supervised model with parameters learned by the unsupervised model trained on the same inputs. Again, using model to do the training on the model. It's like I use the rings to destroy the rings. So we can go to the next section. Yeah, the next section. Okay, so we have still quite a number of pages left. So now we discuss about algos with adaptive learning rates. You might have heard of AdaGrad and all those we will be discussing now. The gist of this section is that algorithms like AdaGrad, RMS prop, and Adam automatically adjust the learning rate for each individual parameter based on historical gradients. So things like automatically adjust learning rate for each individual parameter based on historical gradients. Huh? What's the conclusion? What are these things? What are the pros and cons? Well, these are excellent and they're robust. Currently, the most popular family of optimizers in practice. All the things discussed here. How they are used? Well, Adam and RMS prop are exponentially weighted moving averages of square gradients to scale updates requiring less manual tuning of the learning rates. That's how they are used. So let's start discussing them. The grad, also known as adaptive gradient, it inversely adapts the learning rate for each parameter based on how frequently it is updated. It's based on frequency. Rarely updated weights, you know, if the really updated weights, then large learning rate. If it is frequently updated weights, then smaller learning rate. And there's also RMS prop, which means just root mean square prop. At a grad accumulates all past squared gradients, learning rates may shrink and stop learning. So one problem with AdaGrad is that it accumulates all the past squared gradients, meaning the learning rates may shrink and stop learning, which is why we have RMS prop. RMS prop is only the recent history. Okay, RMS prop uses only the recent history. Root means square propagation. That's what it stands for. Something better than all this would be Adam, which is basically RMS prop plus momentum plus some extra tweaks. Adam is yet another adaptive learning rate optimization algorithm and is presented in here. The name Adam derives from the phrase adaptive moments. Just adaptive moments. It's not Adam and Eve, guys. In the context of earlier algorithms, it is perhaps the best seen as a variant on the combination of RMS prop and momentum with a few important distinctions. Now, the RM is also can be called as like RMS prop with memory from momentum for faster convergence. It can be called as RMS prop with memory for momentum for faster convergence. Now, for those of you if anybody is forgetting what convergence means, convergence is when models loss function performs models performance convergence is when the model's performance stops improving significantly. Okay, when it's stable, that's when the convergence happens. Now, how do you choose the right optimization algorithm? Well, if you remember no free lunch theorem, there is no consensus on like there is no universal law. You need to experiment. You need to dig deep, and that's the only way. Okay, that completes that. And we can move to the next part here, which is Fox second order methods. The gist of this section is that the methods like Newton's or LBFGS use second order derivative, which the converts information to find the object's minimum code directly. Now the conclusion is that this does have some pros and some cons. They are often too computationally expensive for huge deep models and can be attracted to saddle points. So we don't actually use this. Okay, we do not use this. And instead, alternatives are to use first order adaptive methods like Adam. That's instead. So Adam is just better than this. Because this is just computation expensive. So there's Newton method here, and there is a saddle point and all that. There is conjugate gradient. All of that we don't use it. There's also BFGS, Croydon Fletcher Goldfarb Shano algorithm, which attempts to bring some of the advantages of Newton's method without computational burden. It's similar to conjugate method, but it takes more direct approach to approximation of Newton's update. There's also limited memory EFGS, which costs less than the original BFGS, and as we saw, these are not used today. These are just less used, and it's better to just use Adam instead. Coming to 7th, optimization strategies and meta algorithms. Meta meaning something that's used on top of what we already have. Many optimization techniques are not exactly algorithms, but rather general templates that can be specialized to yield algorithms, or subroutines that can be incorporated into many different algorithms. Basically, we may talk about batch normalization. The gist of this is that higher level strategies like batch normalization reparameterize the network to standardize hidden unit activations, stabilizing the learning process. Conclusion is that this section techniques discussed here or templates discussed here rather are extremely effective, considered as standard best practice for deep networks. They still use it today, and it's by normalizing the mean and variance of activations within each mini-match during training. Let me stretch my legs a bit. So again, this optimization strategies and meta algorithms. This is this subsection has actually some interesting topics in it, and let's first get into the first subtopic, which is batch normalization. Here, this is one of the most exciting recent innovations in optimizing deep learning neural networks, and it's actually not an optimized algorithm at all. Again, the many things discussed here are more like strategies or templates rather than actual algorithms. So that's why we're calling strategies or meta algorithms. Which can be specialized to yield algorithms or subroutines that can be incorporated into many different actual algorithms. It is a method of adaptive reparameterization motivated by the difficulty of training very deep models. Again, it's adaptive reparameterization. Okay. Reparameterization. This basically normalizes mean. Okay, this normalizes the mean, and the standard deviation of a layer's activation function within each mini batch. Within each mini batch, stabilizing input statistics for subsequent layers and simplifying the learning process. Batch normalization has thus made this model significantly easier to learn. The conclusion is that this is extremely good. It's a standard practice that significantly stabilizes and speeds up training of very deep models. Again, very deep models. Emphasis on that. The usage is it's done by replacing activations H with a normalized version, as we discussed, as we written down here. Then applying learn parameters gamma and beta to ensure that the model can still represent the same family of functions with easier learning dynamics. Let's go to the other one, next one, which is coordinate descent. The gist of this is the strategy. This strategy minimizes a function by adjusting one variable or a block of variables at a time while keeping the others fixed. And this is effective when variables can be separated into groups with isolated roles, but not effective when variables are highly dependent on one another, leading to a very slow progress. And this is more called as block coordinate descent, refers to minimizing respect to a subset of variables simultaneously. So take a block of variables and change them. While keeping others fixed. This function describes a learning problem called sparse coding. The goal is to find a weight matrix that can linearly decode a matrix of activation values H to reconstruct the training set X. Most applications of sparse coding also involve weight decay or a constraint on the norm of the columns of W in order to prevent the pathological solution with extremely small h and large W. So this is not that good. Like we said, this is only good in some cases, not others. This is especially not good when the one variable strongly influences the optimal value of another variable, as in the function f of x equals, yeah. And we can give an example, but we'll skip that. But this first time encourages two variables, yes. So yeah, we can go to the next one, which is Polyak averaging. What is this about? This method averages together the points in parameter space visited by an optimization algorithm during its trajectory. What's the conclusion? Is it really good? Yes, this is generally good as it helps the model settle in the bottom of a valley rather than leaping back and forth across. And it is still used today. How is it used? Well, in non-convex deep learning, it's typically implemented as an exponentially decaying learning average of the parameters. So this Pollack averaging was invented by Pollack and Judith Sky in 1992. This consists of averaging together several points in the trajectory through the parameter space visited by an optimization algorithm. So let's say there are points, this is the optimization algorithm. This is the trajectory parameter space. Okay, now you take the average. That is this method. This is called Pollack averaging. Um, on some problem classes, such as gradient descent with applied convex problems, this approach has strong convergence guarantees. Can go to the next one, which is supervised pre-training. Now, if you've gone through the LLM lecture of Andre Karpathy or my own lecture, which is copied from Andre Karpathy, you would recognize that this is the third step in. Okay, this would be the second step in the creation of LLMs. First being unsupervised pre-training, second is supervised post-training, and third being reinforcement learning post-training. The gist of this is that it involves training simple or shallow models on a task before moving to the final complex model, providing a better starting point for optimization process. It's kind of like giving a vaccine. And the conclusion is that it's good for providing guidance to intermediate layers, though it has been partially replaced by other architectural innovations. However, it is still useful tool for some difficult tasks. How is it used? Well, it is done through greedy layer-wise pre-training or the fitness approach. So we are using a greedy thing here, where a teacher network provides hints into a deeper student network. So this is where some of the things get interesting. Sometimes directly training a model to solve a specific task can be too ambitious if the model is complex and hard to optimize, or if the task is very difficult. It is sometimes more effective to train a simpler model to solve that task than make the model more complex. So again, this is kind of like a proverb here. So sometimes I'll repeat it. So when I was directly training a model, to solve a specific task can be too ambitious if the model is complex and hard to optimize, or if the task is very difficult. It is sometimes more effective to train a simpler model to solve a task than make the model more complex. Now, if you have a hard model, if you have like a complex model, optimizing it is it's hard. It's hard to take a simple model and then optimize it. It's much easier, and then make it complex. So these strategies that involve training simple models on simple tasks before confronting the challenges, training the desired problem, the desired task is culturally known as pre-training. Greedy algorithms make the problem. So we use greedy here. So greedy breaks the problem into many components and solve for the optimal version of each component in isolation. And pre-training and especially greedy pre-training algorithms are ubiquitous in deep learning. This section we describe especially those pre-training algorithms that break supervised learning problems into other simpler supervised learning problems. This approach is known as greedy supervised pre-training. Greedy supervised pre-training. Another related line of work is the FitNets by Romero et al. In 2015. This approach begins by training a network that has low enough depth and great enough width to be easy to train. This network then becomes a teacher for a second network designated the student. The student network is much deeper and thinner and would be difficult to train with STD under normal circumstances. The training of the student network is made easier by training the student network not only to predict the output of the original task, but also to predict the value of the middle layer of the teacher network. This extra task provides a set of hints about how the hidden layers should be used and can simplify the optimization problem. So we will revisit this idea a bit sooner, or a bit later. So the next section would be designing models. Designing models to aid optimization. How do you design the models to aid optimization? Well, this is a principle that optimization is often improved by choosing a model family that is naturally easier to optimize than by changing the optimizer itself. Again, this follows just the same thing that we just said. This idea is essential and foundational. The philosophy drives the design of almost all modern neural architectures. It is the primary way deep models are scaled today. So how is this done? Well, one of the ways is by skipping connections to shorten paths for gradients or use auxiliary heads that provide additional hints to lower layers during training. So in practice, it is more important to choose a model family that is easier to optimize than to use a powerful optimization algorithm. So again, to reiterate the same thing, choose a model family that's easier to optimize. Than to use a powerful optimization algorithm. Now, that's not recommended. So, if you remember Elon Musk's engineering mantras, he says make the problem easy and delete the things. So, when you have a kind of like a project, you need to delete the code and crunch it down to smaller as much as possible, because then it's easier to optimize it and improve upon it. If you have a complex one, it's hard to optimize it. So specifically, modern neural networks reflect a design choice to use linear transformations. This again is why we use why transformers are famous, because they're linear. They are linear. Help parallelization. Okay, parallelization is not the topic here. And models have nice properties that make optimization easier. And in other words, modern neural nets have been designed so that their local gradient information corresponds reasonably well to moving towards a destined solution. Linear paths or skip connections are some other strategies you can use. You know, to reduce the length of the shortest path from the lower layers parameters to the output, and thus mitigate the vanishing gradient problem. Can use also auxiliary heads and all that. Next is continuation methods and curriculum learning. Well, these methods in this subsection construct a series of increasingly difficult versions of an objective function or a trained data in a solution of an easy version to initialize the next. This is highly effective for complex AI tasks, and it's well used in research. So this is where we use the curriculum learning. So this is how the teachers learn. They are similar to the simulated annealing. If you know how glass is made, like how how glass is made, they use simulated annealing where the temperature is high and low, and then it's gradually decreases like that. And we also use relaxation methods here, meaning or continuation methods. These are just a family of strategies that can make optimization easier by choosing initial points to ensure that local optimization spends most of its time in well-behaved regions of space. We're relaxing the constraints, so within that, it plays around. The continuation methods were mostly originally designed to deal with the problem of local minima, local maxima. The local minima are no longer believed to be primary problem for neural network optimization. Fortunately, continuation methods can still help. The easier objective functions introduced by the continuation method can eliminate flat regions and decrease variance in gradient estimates and improve conditioning of the SL matrix, or do anything else that will either make the local updates easier to compute or improve the correspondence between local update directions and progress towards a global solution. Curriculum learning is one of the most interesting ones that I found. Proposed by the author and his group. one of the authors, is Bengio et al. In 2009. They observed that this approach, curricular learning or shaping, can be interpreted as a continuation method. Basically, what you do is you first plan on learning, you begin by learning simple concepts and progress to learn more complex concepts. So, simple concepts and complex concepts that depend on the simple concepts. This is how curriculum is based. This is how your school curriculum is based. And this method was known to accelerate progress in animal learning. And Bengio justified this strategy as a continuation method where earlier cost function are made easier by increasing the influence of simple examples and experimental demonstrating that better results could be obtained by following the curriculum on a large-scale neural language modeling task. The curriculum learning was also verified as being consistent with the way in which humans teach. Teachers start by showing easier and more prototypical examples and then help learn and refine the decision surface with the less obvious cases. Zaremba and Sutskever found that much better results were obtained with the stochastic curriculum, in which a random mix of easy and difficult examples is always presented to the learner, but where the average proportion of the more difficult examples, here those with the longer term dependencies, is gradually increased. With the deterministic curriculum, no improvement over the baseline was observed. So the Ilya Sutskever and Zaremba, the Ilya Sutskever, the legend, also famous in the various memes. They discovered in 2014 this stochastic curriculum, where the same thing, except you also provide some difficulties, and the difficulties keep increasing with these are difficult examples mix. I just increase their proportion and the proportion and the amount of difficulty. That completes that set. We have now described the basic family of neural network models and how to regularize and optimize them. In the next set of videos, if I make them, we will turn to the specializations of the neural network family that allow neural networks to scale very large sizes and process input data, and that has a special structure. The optimization methods discussed in this chapter are often directly applicable to those specialized architectures with little to no modification. Now, the only thing that is left now are the only main concepts in this book that are left are like convolutional neural networks and recurrent neural networks. Now, recurrent neural networks are not that used, so we may be proclivated to kind of skim faster or skip that chapter, but we will see that, and we'll try to cover it, or we may not get to cover it. It's not important to go through all these line to line. It's more important to actually get at least some grip on it and then start experimenting it. Again, experimenting in actual coding beats everything. So by now, I think we have mostly completed everything, all the important things that we need to know. We have covered enough area. We didn't cover everything, but we have covered enough to stop this here. And this may be the end of this series, or maybe not. Regardless, this has been useful, I hope.